Good afternoon, this is Schweitzer, and we're going to look at a little more complicated example of an elastic collision. So first of all, it has a neutron is moving with a velocity of 3 times 10 to the 6th meters per second. It makes a head-on collision with a stationary helium particle. So this is helium, this is a neutron. So this neutron has a mass of 1 AMU, and if you're in chemistry, you might know that helium can vary, but we're saying it's 4 times heavier. So it doesn't vary a whole lot in nature. Let's call it 2 protons, 2 neutrons, so 4 AMUs. Alright, this velocity is 3 to the 6th meters per second. Okay. What's the velocity of each particle? So essentially, this lighter particle will travel, strike the stationary particle, transferring some energy to it. Helium particle can then continue on its way, and the neutron particle could technically continue forward as well, or could rebound backwards, or just sit still. So again, the rebounding neutron particle could simply, after the collision, sit still, velocity equals 0. It could still be traveling in this direction, velocity positive, or the neutron particle could rebound back, negative velocity. So in this case, how do we solve this problem? In the end, we do end up having, for conservation of momentum, we have the momentum initial is the momentum of the neutron plus the momentum of the helium particle equals momentum final, which is the momentum of the neutron plus the momentum of the helium. So mass times velocity of the neutron plus the mass times velocity of the helium equals the mass times velocity of the neutron plus the mass times velocity of the helium. So we know we have 2 missing pieces. Everything else we know. This momentum initially, this guy, is not moving, so it's 0. We do note that we know the mass of the particles, and we know this initial velocity. So this is a known factor. But the problem is that we have the mass of these guys, but we don't know the velocities, and they very well could be different. To solve this problem is just an algebra problem. What we'll use is a conservation of energy, where the kinetic energy initial is going to, because it's an elastic collision, will equal the kinetic energy final. And this is 1/2 mv squared of the, let's say, the helium plus the 1/2 mv squared of the neutron equals the 1/2 mv squared of the helium and plus the 1/2 mv squared of the neutron. And what we'll do with this problem in a nutshell is we'll have more than one variable. So we'll solve this equation for a single variable and substitute in for one of these guys to remove a variable, and then you can resolve for your missing variable. We're down to 1. So we'll be using substitution to solve this. Because this is just, in the end, for our purposes, is a exercise in algebra, we will just simply give you 2 formulas. Okay? This is where all the math is done for you. So at some point you could determine A and B, and at that point we have 2 formulas that will be given to you in class or right now. So in this case, the problem says what is the final velocity of A and the final velocity of B. So I could label this as A, and we'll label this one as B. Okay. And I want to know what is the final velocity, let's say, of A. So A, let's try this. So VF of A equals the momentum of A, which is the mass of the neutron, times the velocity initial of the neutron, and then the momentum of the B particle is 0. It is completely elastic. So I'm going to plug in these values. Is completely elastic, okay? And then we're multiplying of subtraction here. Velocity of B initial, which is the neutron. I'll try to put this N here. Neutron. Well, the B would be the helium, which is 0, helium. And then minus the velocity of A, which is the neutron, times the mass of the B particle, which is going to be the mass of the helium particle, divided by the mass of A, which is the mass of the neutron, minus the mass of the, see the plus sign here, plus the mass of the neutron particle, helium particle. So just got to keep that straight. So the mass of the neutron, which is A, is going to be 1. Velocity is divided above, which is 3 times 10 to the 6th, 3e to the 6th meters per second. So this whole thing ends up being 3e to the 6th meters per second, plus 1, because it's elastic collision. And then velocity initial for the helium, for the B particle, the B particle is the helium, so that would be 0 minus the velocity of the neutron, which is 3e to the 6th. Okay, that's that thing. And then we're going to multiply this guy times the mass of the helium particle, which is going to be 4. All right, there we go. So this gives me negative 12e to the 6th plus 3e to the 6th, positive. All right. And then at that point, we would divide this thing out. So I have parentheses here. All right, so subtracting those two guys is going to give us a negative 9e to the 6th divided by, add our two masses together. This is mass of the neutron is going to be 1. This is going to be 4. So add together, divide by 5. So we will get a negative value here. And the negative value means that it will be moving, it will bounce back to the left. All right, so it's 9/5 e to the 6th, and 9 divided by 5 is 1.8. So it's 1.8 e to the 6th meters per second. Okay, and it's traveling to the left. This is exactly how we would solve the other one. Okay, I'm not going to walk through this because it's just an exercise of substituting in and solving. One thing just to highlight, I would just mention, is that we have a stationary particle, the helium particle, and then we have another particle that's moving, the neutron. Because neutron's 1, this guy is 4. Being the larger mass will cause the neutron to rebound back, and this guy will just continue forwards. If we had a neutron bouncing into another neutron, okay, the neutron is stationary, this guy is moving. In that case, the aftermath, neutron A, neutron B, neutron A would at that point be stationary, and neutron B would be moving. In this case, that's because they have equal masses. If, in fact, the other way around, we had the helium particle, okay, moving, and the neutron is stationary, then the aftermath of this thing would that not only would the helium particle be moving, but the neutron would also be moving. So the relative masses makes a big difference. Okay. Now the last question on here that I typed in here is, what fraction of the kinetic energy is lost to the stationary particle? To solve this problem, you would need to solve for the velocity of that particular particle. And then at that point, you could say, okay, initially, what is my kinetic energy initial? So kinetic energy Initial is 1/2 mv squared. Now again, initially we have the neutron and the helium particle. Since this guy is not moving, it doesn't have any kinetic energy. This is 1/2. The mass of the neutron is 1, and then 3e to the 6th squared. This would give you your total kinetic energy before. Afterwards, you want to know, okay, how much of this energy, because it's elastic, all energy is conserved. So this will equal the energy of the neutron, even though it's going that direction, and the energy of the helium particle going in this direction. Do a 1/2 mv squared on that guy once you solve for its velocity, which is pretty straightforward just by plugging in your values. At that point, you'll get a kinetic energy for this guy. And what fraction of the B is of this guy? So I'll take kinetic energy B divided by the total, which is just this guy, and I'd get my percentage, and times 100 would give it the actual percentage. All right, look for these formulas in our chapter, and we'll be using them. Thank you.